Hi, welcome to Makino, and thank you for joining us. My name is Mike Boyd, and I'm the Quality Control or Inspection Metrology Services leader here at Makino. I'm standing in our integration bay in our North and South American headquarters in Mason, Ohio, just between Cincinnati and Dayton. Today we're going to be talking about a service that's often taken for granted and sometimes overlooked, and that is our Inspection Metrology Services. Now, this is not a direct service. Rather, we are a service that supports our direct engineering services. So our promise of performance doesn't just end with our incredible Makino equipment. No, our engineering services are really second to none. And they add not only value to your equipment, but they provide an optimized, complete production solution. Now, our teams of engineers, we have multiple teams of engineers who are dedicated, passionate, and empathetic to providing the very best solutions for you. Now, a big part of those solutions is verifying and validating the quality aspect. That's where we come in. We provide the means to inspect that quality of those engineering services. So our primary focus is supporting those turnkey and integration projects. We provide those inspection capabilities so we can inspect the parts coming off the equipment here at Makino. The next thing we do, we provide support to machine validation test cuts. Say you don't want to purchase a complete turnkey solution, but you want to verify that our equipment is capable of producing a particular cut. We will inspect the parts coming from that test cut. We also support our research and development group with inspection needs. And then lastly, we have an in-house gauge calibration service where we're capable and we do calibrate our own gauges. Now, these gauges are used for machine installation and our customer support teams. So today we're going to meet three of our outstanding quality engineers. They're going to provide the insight into our inspection capabilities to show you the depth and the breadth of what we provide. Specifically, we're going to cover three topics. And the first is our inspection equipment. The second is our inspection process, very detailed inspection process. And then lastly, we're going to talk about our capability analysis. And at the end of this presentation, it's going to be clear that our promise of performance doesn't end with just our incredible Makino equipment. Now, some housekeeping. If you look at the top right corner of your screen, you'll notice a chat button. And throughout the course of this presentation, you can click on that chat and ask us any questions or provide any comments. And then at the end, we'll try to address those questions. So let's dig in. Let's now talk about our incredible inspection equipment we have available here at Makino. Let's go. First, let's talk about our precision measuring equipment we have here at Makino. We have 6 large CMMs or coordinate measuring machines, 3 of which are less than 5 years old. And our most recent acquisition we're pretty excited about, and that's our Zeiss 121810 Acura. We also have 3 different types of CMM software. Obviously, the Zeiss Calypso, the Renishaw Modus, and then the Hexagon Quindos. We also have some manual gauges available to include a very large 12-foot by 6-foot surface plate. So I'm here with one of our outstanding senior quality control engineers, Matt Dickinson. Hi, Matt.
Hey, Mike. How you doing?
Great. Thanks for joining us. So if you could please talk a little bit more about our inspection equipment we have here available at Makino for our customers.
Of course. As you mentioned, most of our measurements are done on our 6 CMMs, and we run 3 different softwares on those. That would be Calypso, Modus, and Quindos. Our 2 largest CMMs are 122010s. Those numbers are the lengths of the X, Y, and Z axes in decimeters. One of them has an infinitely indexable Renishaw Revo head and runs on Renishaw's Modus software. The infinitely indexable head is extremely convenient for complicated parts with features as it can measure at any angle using a single calibration. This allows us to measure entire parts with only a few probes.
So Matt, yeah, we just got, like I said, we just got this Zeiss Acura CMM. We're, again, very excited to have. Can you talk a little bit more about that?
Yeah, and that's actually our second Zeiss Acura. And they're both 12-1810s, which is slightly smaller than our other two that I had just mentioned. And they are both Zeiss Acuras, which run on Zeiss's Calypso software. We have a number of repeat customers that provide us with their Calypso programs in order to ensure the part is being measured exactly how they want. We even have 2 customers that provide us with the exact probes they use in-house. One of the neat things about these CMMs is that the heads can be swapped between a fixed head and an indexable head, adding flexibility. And our most accurate CMM is slightly smaller at 12-1610. It's a Lights Hexagon PMM, which runs on Hexagon's Windows software. It has the highest accuracy of all our CMMs, and we use it for parts with the tightest of tolerances. We've been able to hold 5/10 profiles, true positions, and diameters with ease on this CMM.
So we have quite the variety of CMMs here available at Makino.
Definitely, lots of options.
How big of a part can we fit on our CMMs?
One of our CMMs has a weight capacity of 3,900 pounds, although the closest we've ever gotten to that is a 2,000-pound titanium test block.
That's a large part. We're talking
very large.
Probably for aerospace, is my guess.
Definitely. Had to use a crane to load it on there. Typical automotive parts have features on 5 or 6 sides, and you want to leave clearance on each side for probe changes and safe clearance moves. We've had several parts where the clearance moves come within millimeters of the X, Y, and Z axis limits. Many of these larger parts are housings that require deep reach. One such part measured approximately 300 by 350 by 650 millimeters and required a probe reach of over 600 millimeters to get all the features.
So along with the variety of our CMMs, we can also fit a variety of sizes of parts and different parts on them.
Mm-hmm.
So when it comes to fixturing, Matt, we don't run production here at Makino. We see many different types of parts and different projects, and we have to fixture all of them. Could you talk a little bit, please, about the fixture and what we use here for that?
Yeah, definitely. We have a large selection of fixture plates and modular fixture components, and we can use them to build pretty much anything we want. We typically build very minimalistic 3-2-1 style fixtures, and we've fixtured everything from knife blade holders to large converter housings using those components.
So with our CMMs, our inspection equipment, the modular fixturing, say we get a part in with some tight tolerances, which we usually do. Say a tolerance of a 25 micron true position, or something like a 10 micron total tolerance on diameter. What gauge might we use that we have available here at Makino?
For that 25 micron true position, you're always going to want to go with a CMM. Any true position size, really, you want to go with a CMM. It's definitely the best way to do it, and any sort of alternative measuring method is just going to pick up inaccuracies because you're not going to be able to really pick up the datum structure or even sit on it. And for that 10 micron diameter tolerance, I prefer to use a bore gauge over a CMM. In my experience, you'll get a more accurate reading with the bore gauge, especially if it's a custom-built air gauge. However, a CMM will still be very precise, but you'll likely see a slightly different value. This is due to the differences in how the diameter is physically picked up. In most cases, the difference will be a maximum of 5 microns, but that's not great if 5 microns is half your tolerance. The key is to pick a measurement method, dial into it, and stick with it.
Now often, we'll use customer supplied gauges. We like that, and that allows us to use the actual gauge they're going to use in their production environment. So things like you mentioned, that tight diameter tolerance, often we'll get that custom gauge that measures just that diameter for the customer.
Yep, definitely helps things go a lot smoother when we get to their facility.
Now, out of all these CMMs that we're talking about, which ones have scanning capability? How many? And what's the advantage to scanning?
4 of our 6 CMMs have scanning capabilities. There's a number of advantages to a scanning CMM. In my opinion, the greatest benefit to scanning is picking up the entire feature. A 3, 4, or even 8-point circle might pick up only the high or low points, giving an incorrect diameter. By scanning, you pick up the entire feature and get a more consistent measurement. We default to a density of 10 points per millimeter, which can quickly add up to thousands of points per feature. Scanning also makes it easy to output detailed form plots, which can help identify machining issues such as hole lobing, entry and exit error on milled features, and local flatness spikes. Flatness also allows you to pick up complex surfaces and output profile plots. This can help generate not only X, Y, and Z offsets, but also A, B, and C offsets to help you dial in.
Well, thank you, Matt. Thank you for joining us, providing the insight to our inspection equipment here for our customers at Makino.
Of course, anytime.
So it's clear that we have many precision measuring equipment resources here at Makino available for our engineers and ultimately you. It shows our commitment, the level of investment that allows us to keep that promise of performance. So next, let's talk about our very detailed inspection process. Let's go. So let's talk about our inspection process. So many steps to our inspection process. Not only are we designing a new machining process, we're also designing a new inspection process. And we believe that the inspection process is just as important, if not more so, than the machining process. Because if our engineers don't have confidence in the data that they get back from the part inspections, they can't make the proper adjustments to the process. Another one of our outstanding quality engineers here at Makino is Dan Westerheide. Hello, Dan.
Hi, Mike.
Thanks for joining us.
Happy to be here.
Would you please provide a little more insight to the multiple steps it takes to design and create that inspection process?
Designing an inspection process for a new turnkey project that is reliable and gives us good data is key to project success. We will either be given or will create a dimensional control plan. This gives us our clear roadmap to project success in terms of quality. The DCP is going to not only give us the requirements for part print, but also the statistical requirements for the entire run of the project.
So talking about that dimensional control plan, or DCP, it's really a roadmap, and it's a very important document. What other key piece of information on that DCP is critical?
Not only does it identify the feature and the tolerances associated with it, but it also identifies what gauge we need to use. Sometimes we won't use a CMM. Sometimes the customer will provide a hard gauge that we will use to collect data on that feature.
And as I mentioned earlier, using a customer gauge is preferred in a lot of cases because that's what they're going to use in production.
Exactly.
So what's next after you create that DCP?
So after we create the DCP, now it's time to create the actual CMM program. So using the machine datums that we're using in the machining process, we will create what is called the base alignment. It's our base coordinate system for the CMM program. We will iterate that base alignment 3 times. That will allow us to dial into each part very accurately to ensure that the data that we are getting is very good. So now that we've got the CMM program itself created, now we've got to create the fixture to hold the part. This is a very critical part of the process. We need to ensure not only that it's static and the part is not going to move, but it's also going to locate the same each time we load a part on there, and also those main machining datums in that base alignment are exposed so we can measure them in the process.
And we talked earlier about our fixturing that we have here available to us. It's very modular because we're always changing. We're not running production, we're going in and out of different projects.
Right, so each project has a different fixture. A lot of times we use a method called the 3-2-1 method to build the fixture. It's a proven method that we've had good results with that continues to give us success with our projects and the way we fixture our parts on the CMM.
So now we have that CMM program created in the computer. We haven't really done much of anything out here on this actual CMM other than create the fixture, present the part to the probe. So what's our next step to ensure that we can move around that part safely?
Well, first, like you said, we need to prove out and make sure that we can measure the part safely. We need to make sure we can get all those machining datums, all those features that are in the DCP that we need to measure. Secondly, we need to test it. We need to make sure that when we're measuring a part, that our data is repeating. That is very critical for the application engineer who's using our data from the CMM to make adjustments on the machine.
So, and that is called a gauge R&R or PT study. We'll talk a little bit more about that later when we get into the capability analysis part of it. So what's next after the actual part inspection?
So I touched on, we do these things for the application engineer to give them confidence. At this point in the project, it's taking the data from each part and working with the application engineer and troubleshooting the issues that they have on the machine. We need to take that data and find a way to get our machining process stable.
So when it comes to troubleshooting with that application engineer, you talked about, what some of the things would you do to help them troubleshoot an issue when they see something that they don't expect in the data?
Right, so to verify that the data is correct, sometimes we'll use a different method of measuring on the CMM, whether that's a different probe configuration or a different method of measuring a certain feature call on that DCP. Also, sometimes we will go to the surface plate and we'll measure with hard gauges to verify what we're getting on the CMM is clear and accurate data and we have trust in it.
So now we have this much of the inspection process created. We're checking parts, we're troubleshooting issues. What is one key task that we must perform early on to ensure we're successful here at not just Makino, but at the customer's facility?
It's called correlation, and it's a really, really big step. It's got to happen. We work with not only our application engineers, we work with the customer's quality team to ensure that not only do we have a good CMM process, but that they have one as well. So what we'll do is we will measure a part here and collect data on it, and then we will send it to the customer and have them do the same thing. We then compare the data between our CMM and their CMM. This is to make sure that our measurements are very closely coming out the same way that theirs are. This gives the application engineer confidence that when he leaves and goes to the customer facility on their production floor, that the CMM program and the data he was getting here is very, very closely resembled to what he's going to get when he's on site at the customer's facility.
And that could really save a lot of time in the back end for not just us, but for the customer too, so they're up and running quicker.
Yes, it is a critical step.
All right, so correlation is really key, Dan. So earlier, one of the things I talked about that we provide, and that is support for validation test cuts. We provide that inspection support to measure those parts coming off of the test cuts. We also have in-house gauge calibration capability.
Yes.
Where we actually calibrate our own gauges. Would you please talk a little bit about that?
Yes, so we have our PMM, which measures at a very high rate of precision. It's our most accurate CMM that we have. We do our gauge calibration on that machine here. The gauges that we're calibrating are key to installation success of our Makino machines at a customer's facility. We use these gauges to verify the machine geometries to make sure that the spindle is square with the axes of the machine. This is critical to making sure our machine cuts at a very, very high accuracy rate. So we were able to measure those gauges with our advanced machine to prove that yes, these are high quality gauges and they can be used to perform these machine geometries on our installations.
And as you mentioned, the PMM, that's a very accurate CMM. So it's
Yes.
a precision measuring machine.
Yes.
And that's capable of holding sub-micron tolerances.
Yes.
We have that capability to quickly turn around those gauges. So our installation team, our customer support engineers have that gauge available to them very quickly.
Yes.
So thank you, Dan, for joining us today. And thank you for going into the detail of that inspection process that we could spend a lot of time on, and we could spend hours on explaining each one of those steps. Thank you.
Nope, you're welcome.
So it's clear that we're very detail-oriented in our inspection process, and that allows us to keep that promise of performance. And our inspection process really is second to none. And you will have the confidence to know that that Makino designed machining process is capable of providing the solutions you need for your production requirements. So next, let's talk about that capability analysis. Let's go. Next, let's talk about capability analysis. We mentioned verifying and validating that Makino designed machining process. This entails not only meeting part print, but also meeting a statistical capability. Here we're looking to see if that Makino designed machining process is under control. I'm here with another one of our outstanding senior quality control engineers, Kevin Anderson. Hello, Kevin.
Good morning, Mike.
So thanks for joining us. So our capability analysis, when talking about that's really taking it to a whole new quality level.
Right.
Not only are we trying to meet the part print for those parts coming off the machine, we're wanting to look at that data and analyze it statistically to see if that process is under control. So could you talk a little bit more about, not just meeting part print, but on the capability analysis, how important it is to ensure your gauge is capable?
That's right. It's a very important topic, Mike. Before we can show our customers that our machines can make good parts, we have to give confidence that we can even measure those parts and prove that they're good. And to do that, Makino employs two major methods. We use a GRR study, which is a gauge repeatability and reproducibility, and a P/T ratio study, which is precision over tolerance. Now, usually we use a gauge R&R study when we're measuring bore micrometers, air gauges, and other hard gauges that we know there's going to be multiple employees measuring parts and making changes. And to do a gauge R&R study, we usually use 3 parts with 3 operators, measuring each part at least 5 times, and we calculate that data. Now, when we're using the CMM, we know that it's going to be our quality engineers making most of the measurements and loading and unloading the parts. So we like to use a P/T ratio study, precision over tolerance. Now, to do that, we use 1 operator measuring 1 part and measuring that part 10 different times. Now, we measure all those parts in 10 different runs, and we calculate that data and compare it to the tolerance on the print. And once we compare to the tolerance on the print, we look for if a measurement is using less than 10% of the given tolerance, we know it's a good measurement method. Now, if that tolerance gets into that 10% or 30% range, we might have our quality engineers take a look at that and see if it's going to be a valid measurement method. But we know anything over the 30% tolerance is definitely going to have to be measured in a different method.
So sometimes we have people who take the hard line and really say the gauges have to be less than 10% on the error. And that's just not practical. Not every feature requires that level of precision on that repeatability. Sometimes, like you said, it could go up to 30%. It's just open for interpretation. So part of the statistical analysis and the capability runoffs we're talking about here, there's indices that indicate how good you are and how capable your process is. Could you please talk a little bit about those different indices?
That's right. The 2 major indices we use here at Makino are CPK and PPK, and their corresponding CP and PP. Now, before I touch on the differences between CPK and PPK, I'd like to go into what the difference is just between CP and CPK. Now, CP is a process's potential. Okay, so if we imagine a bullseye for a moment, we think about a bullseye and we're throwing darts at it. And we're not really good dart players. So we've got some shots in the upper left, some in the bottom right, and maybe some got lucky and they hit the center. Now, this would be a low accuracy and low precision shot, which would mean our CP is both low and our CPK is also low. But if we think for a second that we had really consistent dart throws, right? We had a really tight shot here. All 6 shots were just in a really tight circle. But that circle was not on the bullseye. Maybe it was just in the upper left corner. Our consistency was great, right? But our accuracy was not so good. And in that scenario, that would be a high CP or process potential, but still a low CPK because it wasn't centered on the bullseye.
Sure. So we're really talking about like a nice tight shot group represents your CP, and that being centered on a bullseye
That's right.
represents the CPK.
That's right. CP is about consistent data and gives you the potential for that process to be in line, whereas CPK must take the centering to nominal into account.
So a common number, significant CPK value is 1. And what does that represent? What do we usually see as far as requirement from our customers for CPK values?
Great question, Mike. Now, a CPK value of under 1 means your process is out of control and you probably need to do something. Most of our common values that we see for CPK are usually 1.33, 1.67, and the coveted 2.0. Now, 2.0 is a great target, right? A 2.0 CPK value is your 6 sigma. It means your process conformance is 99.99999%. I think I got all of them. Those are a lot of 9s. But essentially what that means is your process in a billion part run is only going to have 2 scrap parts in a billion.
That's crazy.
That's right.
Only 2 scrap parts.
It's a really great target, but that comes with a price. You have to pay for the machine capability. You have to make sure your process is perfectly controlled. And as we talked earlier, you have to make sure your measurement method is going to be able to even see a CPK of 2.0. More commonly, we see a 1.33 and a 1.67 CPK values asked from our customers. And those are also great targets. A 1.33 means that you have a 99.99% conformance, or 63 parts in a million are potentially scrap. And a 1.67 CPK is even better. It means just 1 part in a million could potentially be scrap, or a 99.9999% conformance.
And that's still kind of crazy when you think about that. You have a Makino design machining process who's capable of producing very little scrap. And the higher the CPK value, the harder it is to control.
That's right.
And maintaining that number really could cost you money in your machining process and your production solution. Do you really need to keep that highest level of a CPK value?
Well, it's a cost-benefit ratio, and that's what customers have to decide. Are they able to pay a very high price up front for the higher machines to really try to drive that 2.0, or are they okay with scrapping just 63 parts in a million and be okay with a 1.33 CPK?
And what's important is that we're able to analyze statistically, again, that Makino design machining process. Those parts coming off that Makino here for the customer, we are able to analyze that data and tell them that their process, this design process, is under control.
That's right.
So everybody's burning question. You know it's coming. What's the difference? You mentioned 2 different indices before, CPK and PPK. What's the difference?
Well, it's a great question. It's one that everyone loves to discuss. And honestly, the equations for them are really similar. I'm not going to drive too deeply into these equations, but CPK and PPK are very similar, with the one exception of how the standard deviation of the parts are calculated, or more importantly, how that data is gathered in the first place. Now, PPK, the process performance, is great for production factories. This is a great capability analysis of measuring all the parts that have been run on machines, looking at all those parts over a long period of time and seeing those long-term variables, such as machine degradation, tool wear, coolant. And then you take that data and you calculate it and you get your PPK number. Now, the problem with PPK is it doesn't predict the future, and that's where CPK shines. CPK shows the future process potential. And that's why we like to measure 32 parts from one machine, one fixture, and one nest, all in sequential order, and calculate a CPK value. We can eliminate the variables such as tool wear and machine degradation, and we can predict what the process will actually run in the future. And this is a much more important indice for signing off a machine that we will then install at a customer's facility.
So it's clear that we know what we're talking about here. We know that our Makino design machining process is going to provide that customer the confidence to know that their process has been proven and is capable. So thanks, Kevin, for joining us today, and thank you for that little insight and capability analysis.
Thanks, Mike.
So as you can see, our inspection metrology services here at Makino are comprehensive and both deep and wide. We've invested not only in our precision measuring equipment, but also in many years of wisdom with our outstanding quality engineers. Now, our promise of performance doesn't stop with just good enough. No, you will have the confidence that your machining process has been fully proven. Thank you for your business. Thank you for watching today and joining us. Next, we'll have our question and answer session. And as always, you can contact us via email or phone call. Thank you. All right, greetings everyone, and thank you for attending our Makino webinar, Metrology and Turnkey Solutions. We are live here, ready to take any questions that you may have. Again, thank you for attending. We have Dan, Kevin, and Matt all live here, ready to answer some questions. And we've got some questions that came in. And please, as we go through some of these questions, if you have any other questions, go ahead and throw them up in the chat or the Q&A. So let's see. The first one I've got in here is, what are 321 fixtures? So I'm going to throw that one over to Matt, actually. Matt, if you could answer that question, it'd be great. Thank you.
Yeah. When you're fixturing a part, you want to constrain it completely without over constraining it. And the easiest way to do that is to have it. So for a good example would be starting with a square block. You have 3 points locating on one side. That'll lock you in on one axis, and it'll lock 2 of your rotations in. And then you add 2 points on another side, and that will lock in a second axis and your third rotation. And then a single point on another face will lock in the last axis. And that can translate to non-cubic parts as well. Maybe you've got 2 holes, you've got pins in them. That kind of counts as the 2 and the 1. And then you've got 3 points on another side, and you've got your part perfectly locked in space without over constraining it.
So really, it's like we're mimicking like a basic part datum structure design.
Exactly.
And doing that, the part, like you said, is fully constrained and defined. And we're not actually sitting on part datums, design datums, but we're giving access so we can probe those part datums. Is that correct?
Yeah, and you want to design it to be as repeatable as possible. As you can take one part off, put the next one on, and it'll be sitting in the exact same spot so you can find those datums again.
Awesome. Thank you. Let's see. Another question came in here. Why is PPK better for production, but CPK is what Makino likes to use? And Kevin, our statistical master, I'll throw that one over to you, please. Thank you.
Thanks, Mike. Yeah, I kind of touched base on it a little bit in the video, but I didn't go into depth enough. So PPK is really great at looking at the historical data. So a lot of our production customers, they're not going to measure every single part that comes off the machine because that would just take up so much time. So, their measurement strategy might be to measure every 10th part or maybe every first and last part of a shift. And in that scenario, because they don't have that sequential data, they'll need to use the PPK formula to look at those values. But we prefer to use CPK because we are just much more stringent on how we collect our data. We try to collect, 32 pieces sequentially, one after the other. And then we can use the CPK formula to predict, hey, in the future, this process will be in control and we'll have, whatever certain scrap rates.
Yeah, so, again, the big differentiation is, the CPK is a predictor of what to expect in the future. That index gives us that confidence in what to expect versus PPK. So thank you, Kevin. Let's see. Another question in here. What is the allowable difference in data when performing a correlation study with your customer's CMM output? And I'm going to throw this one over to Dan. Please, Dan, if you talk about correlation. Thank you.
Yeah, so general rule of thumb for correlation studies, or even for the gauge R&R, which we talked about in the video as well, is 10% of the total tolerance. So, for example, if you've got 100 micron true position tolerance, you want to see the measurable amount that we get here compared to at the customer, we want to see less than 10% difference from that. So, less than 10 microns difference between what they measure and what we measure. It's kind of a good general rule of thumb. So for, a feature with a tighter tolerance, that number obviously is going to shrink as if it gets bigger. If it's say 500 micron true position tolerance, well, then you obviously have a bigger range there. So that is usually the good rule of thumb to follow.
Yeah, and what we've seen differences in gauges used between inspections here and at the customer's facility. And we'll see sometimes a greater difference, but as long as they're stable, the values are stable, we can certainly dial into the customer gauge when the turnkey gets delivered. So thank you, Dan. All right, that wraps it up here. So again, thank you everyone for attending the webinar. I hope you enjoyed it. If you have any further questions, please reach out to us through makino.com, and we'll get you linked up with one of our experts here, one of our application engineers, or many other engineers here at Makino. So again, thank you for attending.